This is the start of section 8.5, solving exponential and logarithmic equations. This is going to be a two-part video series, this being video 1 of section 8.5. This video will deal with solving exponential equations and knowing what the three methods are for solving such equations. So a little bit of terminology first. An exponential equation here is simply an equation where the exponent includes a variable. So up to now we've been dealing with equations such as 3 to the x equals y. Well, now we're actually going to give this y value a value and let it equal some value, let's say 81, and we're going to solve for this x value here. So all an exponential equation is, it's just an equation where the exponent includes a variable. One of the actual methods of solving exponential equations involves logarithms, so I figured let's revisit a couple of logarithm rules or logarithm properties and introduce one of our own in this section. If we have two numbers m and n that are both positive, and the value of m and the value of n are the same, then log of m equals log of n. Also, don't forget we also have these following rules because we have these following rules. Because exponentials and logarithmics are inverses of each other, hence they undo each other, we can say a to the log base a of b equals b, and log base a of a to the b power will equal b. If we raise any value a to a logarithm with a base a, they will cancel each other out or undo each other, and we'll be left with our value b. And if we have a logarithm with base a evaluated at some value of a to a b power, we just get b out. So here are the three methods for solving these exponential equations. First step here, first method, is we could rewrite one side of the equation to have the same base as the other side. So we're taking it as one side and rewriting it with the same base as the other side. And you'll see that in an example to follow. Second method is you could take the logarithm of both sides of the equation. And when we say take the logarithm of both sides of the equation, we mean take the logarithm with the same base as you have raised to a power. So if you have like a log base, if you have 2 to the x, if we have something like 2 to the x equals 32, you would take a logarithm with base 2 because you're raising 2 to the exponent or to some variable, unknown variable. So method 2 is you could take the logarithm of both sides of the equation, and you'll see that in a further example. Or, last resort, a little bit more tedious and more complicated, but not that complicated, is method 3. You can use the change of base formula and then solve. So, 3 steps, 3 methods for solving exponential equations. First one, just rewrite one side with the same base as the other side. Step 2, or method 2, you can take the logarithm of both sides of the equation, and then method 3, use the change of base formula and solve. So on to a couple of examples here on solving these exponential equations. First one, we have first example a here, 6 to the 2x power equals 216. Well, if we go by the first method, it was rewrite both sides with the same base as the other. So we have base 6 here, so we have to write this as a base 6. And if you remember, 216 equals 6 cubed. So this equation here can become 6 to the 2x equals 6 cubed. Well, in order for this to be true, the exponents here have to be equal. Our 2x has to be equal to 3. So 2x has to equal 3. And then when you divide by 2, you get x is equal to 3 halves. That's by rewriting both sides with the same base, rewriting 216 as 6 cubed, and leaving 6 to the 2x alone, setting them equal, and then noticing if 6 to the 2x really does equal 6 to the third, then the exponents have to be equal as well. So you set the exponents equal, and you get 2x equals 3, divide by 2, and you get x is equal to 3 halves. Likewise, you could have taken the logarithm of both sides. You could have taken the logarithm of base 6 of 6 to the 2x equals log base 6 of 216. But when you take the logarithm of base 6 of 6 to the 2x, remember that property, if you have a base a to a base a to some power x, then the logarithm and the exponential part cancel, and you're left with a 2x. And then after you evaluate the right side, log base 6 of 216, you would get 3, and x would equal 3 halves after you divide both sides by 2. Next example, we have example B, 3 to the x plus 4 equals 127th. Well, 127th equals 3 to the negative third power. So we can solve it just by saying 3 to the x plus 4 equals 3 to the negative 3 power. Well, if they truly are equal, x plus 4 equals negative 3, and then subtract 4 from both sides, you get x is equal to negative 7. Likewise, you could have taken the logarithm of both sides. You would have had a log base 3 of 3 to the x plus 4 equals log base 3 of 127th. A log base 3 of 3 to the x plus 4, that just becomes an x plus 4 because the logarithm and then the exponential base cancel, and you're only left with the exponent. And then when you evaluate and then set it equal to this here, log base 3 of 127th, if you evaluate that, you will get a negative 3. Subtract 4 from both sides, you get x is equal to negative 7 in both cases. The last example in this part is 5 to the x plus 2 over 5 power. This whole thing, x plus 2 all over 5, is the exponent for this equation. So if you want to rewrite both sides as with having the same base, get 5 to the x plus 2 over 5. 125 is a power of 5, so we can write that as 5 cubed. So if these truly are equal, these sides are truly equal, then x plus 2 over 5 has to equal 3. The exponents have to be the same. So then when you solve for x, multiply both sides by 5, and you get an x plus 2 equals 15. And then subtracting 2, you get x is equal to 13. And then the alternate way you could have done it is take the logarithm of both sides. In this case, you take the log base 5 of 5 to the x plus 2 over 5 and set it equal to log base 5 of 125. Log base 5 of 5, that will go away. These two will undo each other, and you're only left with the x plus 2 over 5 on the left. And then on the right, when you evaluate log base 5 of 125, you will get a 3. And it's the same exact process as before. Multiply both sides by 5, you get x plus 2 equals 15. and then subtract 2 from both sides, you get x is equal to 13. So now the question arises, what if you want to evaluate a logarithm that has any base? What if you want to get a certain value for a logarithm like log base 3 of 20? Well, there's a technique that you can use to find it, because you can't really raise 3 to a power and get 20 like conventionally, like the way we've been doing it. So we have to introduce some sort of new principle or property, or it's more a principle than anything else, or a formula is a better way to say it. You can evaluate a logarithm with any base by using something called the change of base formula. So we can evaluate a logarithm with any base by using the change of base formula. And that's read as follows. If we have numbers m, b, and c being positive numbers, so if m, b, and c are positive numbers here, with our value of b not being 1 and our value of c not being 1, then the logarithm of base b of some number m equals log base c of m divided by log base c of b. So if we have positive numbers m, b, and c, with b not being 1 and c not being 1, then log base b of m equals log base c of m divided by log base c of b. More often than not, our value of c will be 10, as opposed to any other value. So for the rest of this video and the rest of section 8.5, we will be dealing with values of c that are only 10. So in our case, it would only be expressed as log of m over log of b for our case right now. So onto a couple of examples on evaluating logarithms by this nice change of base formula. First one we're asked to evaluate is log base 3 of 15. Now, remember what the change of base is. We're going to take our value of m and our value of b. So b equals 3 and our m equals 15. And since I told you we'll only be working with values of c that are 10, our c value is just 10. So we can write this simply as log of 15 over log of 3. And that's exactly what this logarithm here, log base 3 of 15, is evaluated to. Just simply log of 15 divided by log of 3. Now, one question you may have is, can we divide the 15 and the 3? And my answer is no, because we have this is being evaluated first, log of 15 is being evaluated first, and then we're taking that and dividing it by some value, which is equivalent to log of 3. So these numbers, they won't divide nicely or simplify. And plus you can't do anything with the 15 or the 3. You can't simplify those at all. I will actually be showing you how to evaluate these precisely to a couple of decimal places in a moment or two after the second example here. But for right now, log base 3 of 15 is exactly equal to log of 15 divided by log of 3. For the second example, we have log base 5 of 400. Our base is just 5, our m value is 400, and it's assumed that our c value will be 10. So log base 5 of 400 will equal log of 400 divided by log of 5. And for this one, and that's exactly what log base 5 of 400 is equal to. Log of 400 divided by log of 5. And that is not equal to log of 80, because you cannot take and divide the 400 and the 5, because they're both, only because you're evaluating log of 400 and log of 5, and then dividing. Likewise for log of 15 and log of 3, that is not equal to log of 5. So that's how you evaluate them precisely. Now let's see what they look like evaluated on the calculator, and I'll show you how to evaluate these using a calculator. So now let's evaluate these using a TI-84 graphing calculator. We're looking to evaluate log base 3 of 15. Well, first we need to know where the logarithm button is. And the logarithm button is right here next to the 7 key. So what you're going to do is we're going to evaluate just log of 15 first. So you hit log, and you get that should appear on your screen. And then just press 15 in, close the parentheses, and just hit enter and just notice what value you get. And then likewise you can do it for the same for log of 3. Log, the parentheses will automatically open, and just hit 3, close the parentheses, and hit enter, and you should get those two values. So log base 15 is about 1.176091259, and log of 3 is equal to 0.47712125547. For our purposes, we're just going to be rounding these to 4 decimal places. So log of 15 will just be 1.1761, and log of 3 would just be 0.4771. But now to evaluate what we were asked to evaluate, which is log base 3 of 15, we're noticing that there's a divides there. So I'm going to show you guys the long way first. We have log of 15 opens, and be sure to close the parentheses. Then hit the divides key right here, and then press log again, and then enter 3, close the parentheses, and hit enter. And you should get 2.464973521. But since I mentioned we were rounding to 4 decimal places, just round that to 2.4650, because the 7 will round the 9 up to a 0, which will round the 4 up to a 5. So the equivalent value for log of base 3 of 15, or approximate value, is just 2.4650. Now, if you wanted to, you could have done log of 15, found that value first, hit enter, then hit the divides key, log of 3, close the parentheses, and hit enter, and you would have gotten the same exact result, about 2.4650. So then for the second example, log base 5 of 400, I'm just going to take the log of 400, close the parentheses, hit enter, find some value, and then hit the divides key, and you should get an A and S come up for answer. That'll take this value here, 2.602059991, and then divide it by whatever we're looking for. In this case, log of 5. So hit the log button there, enter in 5, close the parentheses, hit enter, and you should get 3.722706232. And I said we were rounding to 4 decimal places, so in this case that would just be approximately 3.727, just like that. So that's how you would evaluate these logarithms, by using change of base and a nice TI-84 graphing calculator. So now let's solve this equation here. 2 to the 3x power equals 172. Well, first thing that I'm going to do is I'm going to notice, hey, we have a 2 raised to some power and a 172. Second part is, notice 172 is not a power of 2, so we're going to have to take the logarithm of both sides here and try and see what we can come up with here. So if we take the logarithm of both sides, we get log base 2 of 2 to the 3x equals log base 2 of 172. On the left side of the equality, log base 2 of 2 to the 3x, the logarithm and the exponential will undo each other. We're left with 3x equals log base 2 of 172. On the right here, we cannot calculate that directly or evaluate that directly, so we're going to have to use the change of base. And to do that, we get 3x equals log of 172 all over log of 2. Then when you evaluate that by the change of base using a calculator, you get 3x is approximately equal to 7.4662 or 4262. So log of 172 divided by log of 2 is approximately equal to 7.4262. So you get 3x is about equal to 7.4262. Remember, round to 4 decimal places. And now just divide by 3. And get x is equal to, and when you divide 7.4262 by 3, you get a 2.4752. So the value of x that solves this exponential equation, 2 to the 3x equals 172, is just the value of x, that is 2.4752. So just realize when you introduce the log base 2 to both sides, on the left side, or whatever side you have the exponent that has the variable, the log base of 2, in this case, of 2 to the 3x, the logarithm and the exponential will undo each other and just leave you with the 3x. And then when you introduce it to the other side, you're going to have a log base 2 of some non-power of 2, in this case log base 2 of 172. You just realize that you cannot evaluate that one because 172 is not a power of 2. So you have to introduce the change of base to the problem and find 3x is equal to log of 172 divided by log of 2.